Well, this is our lesson today about simple harmonic motion, which in our specification is the topic called oscillations. But most books refer to this as simple harmonic motion, and that is the term that's also used in mathematics if you do this in further maths. The point of this short video is to get you used to the key words that we use when we talk about simple harmonic motion, because what simple harmonic motion does is it takes the oscillation of simple mechanical devices and it makes an assumption about the way that they're going to oscillate. And using that assumption, we can then predict mathematically how they will oscillate in the future, how they will wobble, what might make them wobble dangerously, like a bridge, what might make them wobble rhythmically, like a clock. And that is simple harmonic motion. But in order to be able to use those mathematical equations, we need to start with the words for the terms and what they actually mean in physics. So just two very simple examples of things that move with simple harmonic motion. One is a pendulum that actually is approximated to move with simple harmonic motion. And you can see here a pendulum might consist of a mass, what's sometimes called a bob, and the bob is swinging back and forth like this, like in an old-fashioned grandfather clock. Back and forth it goes, and if left, in the end, it would stop and the thing would hang straight at that point as it ran out of energy. Or better to say, as the energy of the system dissipated into the surroundings. Another classic example of simple harmonic motion would be a mass set to oscillate on the end of a spring that obeys Hooke's law. Now actually, although that seems a kind of a weird thing, that actually things oscillating on springs, that was also used in lots of clocks in more, old-fashioned times, when they put springs in clocks rather than quartz crystals. This is a particularly useful apparatus. This system is used on the International Space Station to measure the mass of astronauts. So if you were an astronaut on the International Space Station and you were worried because you were losing bone mass or muscle mass by not working your legs and your core muscles, well, how do you know you're losing any of your mass? You can't stand on a set of bathroom scales. You won't produce any reading on the scale. And the answer is that you put yourself on a big spring and you bounce up and down. And from the time period of the bouncing up and down, you can then work out the mass of the person. So these are very practical things, and for anybody thinking about doing engineering, this is a solid, good engineering topic. So let's meet these key terms. So here you can see we have a very simple little pendulum device that I've built at home with a piece of string and a large rock from my garden. And I'm just going to pull it from one side and let it go. And here you can see it goes into oscillations, swinging back and forth. Well, there are several simple things that we could measure about this system, and these things come into the equations. One is the time period. How many seconds does it take to do one swing from one, stop, one swing, back and forth? Another one is the frequency. How many swings does it do every second? And that will be measured in seconds to the -1. Another thing we could ask is, if we remember that the rock started at some kind of point like that, its equilibrium point where it would come to rest if left, what's its displacement? How far away in meters is it from its original starting point? We could also ask, what is its speed? Now do notice in the swing, if you watch the rock now for a minute, it has a maximum speed as it passes through the middle, and then it stops at the extremities of its motion. So it's going the fastest as it goes through the middle point, and then it slows down and stops as it comes out to each side. And of course, because we've got displacement and a change in speed, well, the other thing we can ask about is acceleration. What is the acceleration of the rock? Now actually the acceleration is at its greatest when it is furthest away from its equilibrium point. And as it passes through the middle, although it's going the fastest at that point, the acceleration is actually 0 as it goes through the middle point. And that comes from a very simple set of graphs, which, if you know your trigonometry graphs, we're going to look at now. Well, having seen the motion of the rock, we now should be able to produce 3 simple graphs of displacement, velocity and acceleration for the pendulum at each specific point. Well, when we started that little experiment with the stone on the string, the stone was pulled far away from where it started, and it wobbled through the middle, out to the other side, back to the middle and back to where it started, etc, etc. Now if you look at that graph, it looks like a cos curve, doesn't it? A graph of y equals cos of x. Now we can put some other things on, such as this time here, the time it took to do one swing, that is the time period. The time period, the amount of time it takes to go through one cycle of oscillation. And because we also mentioned frequency, let us not forget the equation from the waves topic, that frequency is simply equal to 1 divided by the time period. So we have the time period from this graph, and we can work out the frequency by doing the reciprocal of that number. So what was the velocity? Well, to find the velocity, I'm going to do a simple little trick and say that velocity is the gradient of a displacement time graph. Now look at the gradient. The gradient is 0. It goes large and negative back to 0, large and positive back to 0. In other words, the graph is going to look a lot like this. Whoops, sorry, my line has gone too far. Apologies for the slightly asymmetric nature of that graph, but as you can see, it's a minus sine x graph. But here you can see that it wasn't moving at first as it started. It was moving very quickly in a negative direction as it passed through the middle. It stopped as it swung out to the far side. Then it was moving very fast as it swung back through the middle, but in the opposite direction. And then it stopped again. Now I could carry on this graph, but I frankly don't need to because it's cyclical and therefore just repeats itself. Finally, what about an acceleration graph? Well, I hope you remember from GCSE that an acceleration graph, the gradient of a velocity time graph, gives you the acceleration. So look at the gradient. Large and negative goes to 0, goes to being large and positive. So here we go, we would start off being large and negative to 0, going large and positive, back to 0, and again large and negative. Well, apart from the fact that this graph is a slightly squashed version of that, if you notice, it's been flipped upside down. When your displacement is positive, the acceleration is negative. And when the displacement is negative, the acceleration is positive. And this gives us the defining nature of simple harmonic motion. So here are the variables that we've seen in the motion of the pendulum. Displacement, how far away you are from the original starting point. The velocity and the acceleration, good old-fashioned physics words. Time period and frequency, which you met when you did your waves topic, and also you'll see in the centripetal motion topic. Now what we saw with the graphs is that there is a relationship in simple harmonic motion, and it is this, that the size of the acceleration is directly proportional to the size of the displacement. But the acceleration is always in the opposite direction to the displacement. Now if this is true, you can start from this one point and you can work out the motion of a pendulum or a mass that's oscillating on a spring and predict its motion. That the size of the acceleration is directly proportional to the size or the magnitude of the displacement, but the acceleration is always in the opposite direction to the displacement. If these things are true, the thing is moving with simple harmonic motion.